Again, it's a technical information that is given by our customer, that is decided by us, depending on the type of problem we are dealing with. And this is time 0. And we need to, starting from 0, we need to sum the increment of Q, they might be positive or negative, up to time t. So the integral is from time 0 to time t. During this time span, the increments will be computed for each time step, and time will be varying into this time span from 0 to t. I am computing the increment of Q for small delta t dt. And therefore, I need to make time changing with a variable of integration, which I call tau. So, let me just put the integral sign. Let me go here. Otherwise, you don't see. I just put the integral sign, integral between 0 and t of e 1 over k, e to the power of tau over k, p tau in the tau, where tau is varying from 0, fixed, to t, fixed. And this is equivalent to integral of the second of the right-hand side integral 0t of e to the power of tau over k, 1 over k, q tau, plus e to the power of tau over k, d su dt, d su d tau, sorry, q tau in d tau. And here I have to close around parentheses. Good. Now let's look at what's in. Let's look back at the right-hand side of this equation. What is this? This is the derivative d su dt of qt times e to the power of t over k. Is this true? Let's compute this derivative to check whether it's true that this right-hand side is equivalent to this derivative. This is the derivative of a product. So the derivative of a product, in order to compute it, we have to write it in this way. The derivative of the first times the second unchanged, like this. Okay? So this is equivalent to d ut su d t times e to the power of t over k, which is exactly what I see here. Plus the first unchanged, qt, times the derivative of the second. The derivative of the second, it's equivalent to, it's equal to, again, e to the power of t divided by k times the derivative of the exponent, which is 1 over k, which is what I find here. Here, sorry. So it is indeed true that the left-hand side is equivalent to this derivative. Okay, good, but then I can substitute. This is an integral of something that can be written as a derivative. So the result of the integral is just the argument of the derivative. So I can rewrite this long integral here in a more compact form, because I can substitute the integral of a derivative with the argument of the derivative. Okay, let me do that. But in order to do that, I have to clean the blackboard. Fine for everybody. Okay. So let me rewrite the left-hand side. Okay, so I just copy it, integral between 0 and t of 1 over k e to the power of tau divided by k p tau in the tau, which is equivalent to the integral of the derivative. So this is qt, q tau, sorry, 2 times e to the power of tau over k computed between t and 0. Then let me compute this result of the integral between t and 0. This is equal to qt e to the power of t divided by k minus, if I substitute for tau 0, e to the power of 0 becomes 1, and therefore this reduces to minus q0. Okay, Q0, what is Q0? It's the river flow at time 0. It's something that I must know. It's the initial condition. Again, we know that to compute an integral, we need to know the initial condition. Okay, fine. But what is the variable we are interested in? We are interested in Qt. So let me compute it explicitly. Let me bring Qt at the left-hand side. Qt is equal to okay, I need, in order to get an explicit representation for Qt, I need to divide everything by e to the power of t over k. Okay, so first let me write at the right-hand side Q0 times e to the power of minus t divided by k. Okay, because I need to divide Q0 by e to the power of t over k, and therefore this is equivalent to multiplying Q0 by e to the power of minus t over k. Look, this is a depletion term. This annihilates, vanishes for increasing t, which is fine. The initial condition, the effect of the initial condition, it's something that vanishes as I move forward in time. This is perfect. You may assume that Q0 is equivalent to 0 if you wish. If you start well in the past, your simulation, then by considering that in any case the effect of the initial condition is not long-lasting, you can assume that Q0 is equivalent to 0. But for now, let's keep it, okay? And then I have to sum this integral plus. And what is this integral? This is the contribution to river flow that is given by rainfall. You see that there is rainfall here. Okay, so we have a term that is the effect of the initial condition, and then we have a second term, which is the rainfall runoff part. Okay, don't forget of dividing inside the integral by e to the power of t over k. Okay, so let me write integral between 0 and tau of 1 over k p tau and then we have e to the power of tau over k divided by e to the power of t over k in the tau. Good. Okay, now we can write this term under integration in a more compact form. And let me write the final relationship for the linear reservoir model. So we can say that Qt is equal to, let me put the integral first, the integral between 0 and tau of 1 over k, which is a constant, p tau, e to the power of minus t minus tau. I changed the sign here, divided by k, okay, and in the tau. Okay. Plus Q0 e to the power of minus t over k. Good. Remember that Qt, there was a second equation which we eliminated. Qt is equal to Wt divided by k. This is the second equation that we eliminated. This is the linear reservoir. At this stage, in order to relax a little bit, let me discuss K. What is K? Because we didn't say anything about K. First, let's say that it's clearly a constant. It's a constant because I didn't highlight any dependence on time. So it's a constant. If it doesn't depend on time, which is the only coordinate here we are considering, it means that it's a constant. And what is the unit of K? This is a typical question that I ask at the exam. What is the unit of K? Look here and you can understand the unit. The unit is time. K is, there is a proof which we don't consider, that shows that K is related, is a relative of the time of concentration of the catchment. It's comparable. But we need to introduce some assumptions in order to prove this. We don't prove it because we are not interested. Just remember that k is a constant with the unit of time. Okay. Second, you may look at this relationship and you may tell me, but Professor, we have not finished our job because there is still an integral. Okay, that's true. But what is the reason why I didn't compute this integral? Because, you know, I need an analytical relationship for p tau. P tau is a function, it's observed rainfall. So I cannot integrate something that is unknown. Of course, in your application, rainfall will be known. If you have an analytically tractable function to plug into here that allows you to compute the integral analytically, that's fine. You can compute it. Otherwise, if the problem becomes not tractable because there is no opportunity for analytical integration, you know how to do. It's numerical integration. And the integral, just substitute the integral with the summation. That's fine. Okay, we don't do it now, or let's say, we don't do this substitution of the integral with the summation during our exercises for the linear reservoir. The reason is that we will do that for the next model. So I'm not saying that I leave the numerical integration to you. We will develop an example together, not for the linear reservoir, because for the linear reservoir is simpler than for the next model. But let me give you an example, which is interesting, of a case in which the integral may be analytically tractable. And the case is the simplest case that we may have. Let's suppose that rainfall is constant. Okay, if rainfall is constant, we can of course compute this integral. Let's compute it. Of course, constant rainfall is not a reasonable, I mean, it's not a likely case, but it is instructive because it allows you to understand how a catchment that obeys to the linear reservoir with singular, behaves. How the catchment behaves in very simple situation, in very simple conditions. Okay, so let's forget for now about the fact of the initial condition, and let's concentrate on the integral. And the integral, which becomes qt, is equal to the integral between 0 and t of p constant over k, which is constant, everything is constant p, constant k, which multiplies e to the power of minus t minus tau over k in the tau. And this becomes equivalent, I can bring the constant out of the integral sign, so p over k, which multiplies the integral between 0 and t of e to the power of minus t minus tau over k in the tau. And this is equivalent to p divided by k, something computed between 0 and tau. It is a very easy integral to compute, this one, because it's the integral of an exponential function, so it's very easy. And this is k to multiply the exponential function itself. Probably there is a minus there. Let me think about it. Probably there is a minus. Let me, yeah, I think there is a minus here. Because there is a minus there. Okay, so what is the result? qt is equal to t over k so let's put 0 first. If we put okay, let me put t first. T minus tau, t minus t, this becomes 0. So this is okay. The k here, sorry, here disappears k. Okay, so here I have only t, which multiplies e to the power of 0 is 1, and yeah, I'm sorry, I have not the minus sign because there is a minus here and a minus here, so there was not minus here, so I got a bit confused because I couldn't find the result that I know that we should get to. So do you understand that there are two minus that are compensating each other, so there is no minus. Okay, so let me now substitute tau with t. I have t minus t 0, e to the power of 0 is 1, minus, now I have to substitute tau with 0, so it's minus e to the power of minus t over k. So this is the result. Keep in mind how to derive it, because as I said, it's important, and it's interesting to draw a graph resulting from this. So q tau qt over t along t, and if I indicate p here, I can easily recognize that the river flow, if q0 is equivalent to 0, is something like this. So for constant rainfall, the river flow asymptotically tends to rainfall, which is something understandable. If you think at the tank from which we started, and you put constant rainfall there, even if the tank is empty, because Q0 equal to 0 means that the tank is initially empty, with constant rainfall you get an increasing storage into the tank, an increasing storage, until the storage becomes so high that the bottom discharge compensates rainfall asymptotically. Keep in mind that we don't have any limit to storage in this model. Wt can increase up to any value. This is another assumption that is not really reasonable, but that's fine. I mean, as I said, it's these are a set of assumptions that in a catchment, depending on the behaviors of the catchment, can be justified. Okay, so what is the rate of convergence, of river flow to P? What is the rate? So this convergence is very slow, it's very fast. The rate depends on K, and it's an interesting question. It's an interesting question to ask ourselves whether an increasing K makes convergence faster or slower. I would say that increasing K means slower convergence. If you just look at here, what is convergence? Convergence is ensured by the fact that for increasing time, the second term goes to 0. But if k is small, the second term goes to 0 quickly with increasing time. If k is large, it goes to 0 more slowly. And what is the implication, the physical implication? Increasing k means that you have more storage into the catchment, and means that you have a response of the catchment that is longer. Because if convergence is slower, it means that catchment responds to rainfall in the longer term, not quickly. So the response of the catchment is slower for increasing k. So you have much more storage, and the response time of the catchment that increases, which justifies what I mentioned to you, that k is related to the time of concentration. It is extremely important that you can associate to a model, to a mathematical relationship, a physical interpretation. And this is what I really would like to see in you at the exam. If you prove that you have a perfect awareness of the connections between the math and the reality, then you will get the laud. Because this is what makes an engineer excellent. The engineer is interested in mathematics because mathematics allows us to describe some processes, some natural phenomena in this case, that we need to predict. And this is why math is useful. But of course, in order to make it useful, the engineer must be able to see the connection between the math and nature, in this case, the reality, or the math and the building. A building is not nature, but it's still reality. So this connection is extremely important. So the fact that you see a graph, you don't have to be interested in the graph in the term asymptotic convergence. You have to be interested in what the graph means in terms of what you are describing, what you are required to describe. Okay. That's the linear reservoir, which is based on several assumptions that, as we said, some of them may be reasonable, some others not, depending on the catchment. And therefore, of course, hydrologists are not fully happy with the linear reservoir, and they try to build other models that are more realistic. And one easy extension of the linear reservoir is to make the reservoir non-linear, because this is more realistic. We said that linearity is not a reasonable assumption, and therefore we can make it non-linear. Of course, there are some downsides, and in particular, if you make it non-linear, integration, analytical integration, may not be possible anymore, but you can resort to numerical integration. So this is not really a huge limitation. Of course, numerical integration involves some stability problems that we don't take into account, but you know them. You know that when we turn from a differential equation to a finite difference equation, there might be some stability problems. And indeed, when we will develop our exercises, we may encounter some stability problems. So, here there are a couple of slides with just any steps that I made on the blackboard is summarized in the slides with less details. In the slides, I skipped some of the steps. But, okay, here there is an interesting example of a nonlinear reservoir. For some reason, we don't see, just one second, the bottom of it. Yeah, because the reason is that I changed the setting of the projector. Okay, oops, sorry. I think, yeah, now you can see almost all of it. Just one second. Okay, now you see, yeah, almost all of it. And not all, yeah. Because there is no bottom discharge. There are several ways of, several alternatives in order to make a reservoir nonlinear. First, you may have not a bottom discharge, but a sequence of discharges which are located at different heights, different levels in the reservoir. Removing the bottom discharge is reasonable because you may allow, in this case, the catchment to keep some storage that is not released, which indeed occurs in practice. Think about a lake or a groundwater body that it's not connected with the river. So you may have some residual storage that is always there. And then several discharges placed at several levels. And the discharge from these outflows may be non-linearly related with the water level in the reservoir. So it's up to you. And also you may put a limit to the storage into the catchment, a max storage. And if you exceed the max storage, then any rainfall is immediately converted into river flow. This is possible and reasonable. The only thing is you have to be careful because this is very attractive. One may think of integrating numerically the equations that come out from this. And everything is possible, any solution is possible, but look at the resulting hydrograph because, you know, these additional discharges may originate some sudden steps into the hydrograph. When a discharge is activated, you may see on the hydrograph a sudden increase of the river flow, which may be not reasonable. So you have to look carefully, and also what may happen is some instability, like up and down, because when you reach the level of activation of a discharge, you have a sudden increase of river flow, and then the water level may go up, and then sudden down, and then up, down. So you see some up and downs that are not really realistic. So you have to be careful. But there are several variants of the linear reservoir proposed by the literature. Some of them are also embedded into R as pre-prepared programs. You may try. I'm not really fascinated by the nonlinear reservoir because, you know, I tried several variants and, you know, there are these steps that are indeed creating some hydrographs that are not very realistic. So we're not making any application of the nonlinear reservoir. What instead I would like to discuss with you is another solution which I think is extremely interesting, which is called IMOD model. IMOD, why I'm saying that it's interesting? It's interesting because it's very flexible. Flexible means that it can be adapted to reproducing the behavior of several catchments. It's non-linear, and for many reasons, and it's based on a fundamental assumption and then other more that will be introduced later, other more assumptions. But there is a fundamental assumption that I want to introduce to you. We will not have time today for looking at IMOD in detail, but I just want to introduce the basic assumptions because IMOD, once that you understood it, it's very simple, but understanding the reasoning that brought people to propose it, you know, I think this reasoning needs to be digested. So I think it's a good idea that I introduce the reasoning and then you have a little bit of time to digest it. So the basic assumption is that each point location, let's call it I. So if you have a catchment, you may have several point locations into the catchment. So let me pick up an arbitrary point location into a catchment. And let me call it I. So each point location is characterized by a local value of soil water storage. And let's call it CI. What does this mean? Soil water storage. It means that the soil is like a sponge. It's able to retain some water through infiltration. Not every soil. For instance, if it rains over an impervious soil, the soil water storage is 0. But in general, soil is characterized by pores. It includes pores, so it can store some water. And storing means that if it rains over it, you don't have any runoff, any contribution to river flow. You just have storage into the catchment. And then when the storage is exceeded, the storage capacity is exceeded, then you have runoff. And this model assumes that this soil water storage is different in any location of the catchment. So the catchment has not a unique storage, like in the linear reservoir. You have WT, describes storage for the whole catchment. Here, the assumption is that you have a storage, you can call it potential storage, that is varying. So you may think that this is a distributed model because there is some spatial variability that is taken into account. Yes, we start from a concept of spatial distribution, and then you will see that in order to simplify the model, we find a way to express this spatial variability in a line